Good morning and welcome. So, now we essentially move to the main business part of this course, which are basically divided into two parts. One is this elliptic part, other is the evolution part. For the evolution part, a new theory, the semi-groove theory will also be developed. So, next 7 hours, roughly 14 lectures, we will be discussing about elliptic equations, its weak formulation. So, the whole thing is elliptic equations, few systems, elliptic equations, and weak formulation. So, what are the things where you want to study? The well postedness. Well postedness means existence, uniqueness, continuous dependence. Continuous dependence. Okay. We also study sometimes regularity theory. Some regularity. Regularity is important, as we have already discussed. When the solution you may get it in a some Sobolev space, but you see that whether you can have better growth rate or better H spaces, higher order Sobolev spaces, and eventually even though you will be studying the regularity, the existence theory, and in weak spaces and weak formulation, you eventually want to see whether that solutions are classic. Okay. So, to do this, what we will do is that we study some abstract theory. So, that through the abstract theory you can study various differential equations, and then we will study various boundary conditions, and especially Dirichlet, Neumann, Robin, etc. Okay. We would also like to study Stokes system at least. Some remarks about the Stokes system, which is a system. On this abstract theory, you will see Lax-Milgram lemma, theorem of Stambakia, variational inequality, theorem of Stambakia, equally some variational inequality, and we will also see Babuska-Bessy theorem, Babuska-Bessy lemma, Bessy theorem, useful for systems, In fact, even sometimes the equations can be converted into a system and you can apply Babuska-Bessy theorem. We will make remarks. And then we want to do the spectral analysis. That means eigenvalue problem. And some I hope some regularity we already mentioned, and maybe some maximum principles. Okay, that's the rough aim of this course. Probably in the 14 lectures we will do that, equivalently 7 hours we will do that. Okay. Okay. So, how a general PDE general second order linear PDE is given by, we already mentioned in the first course on PDE. So, L of u is equal to minus, I will be using summation concept here, d square u by dxi dxj and plus ai of du by dxi plus a naught of u, of course equal to f. Okay. So, we use this notation also, dij of u, this we use di of u, okay, eventually, and summation is there basically. Okay. I will not mention, this is a summation convention which we already discussed it. Of course, these are functions of x, a naught of x, functions of x, and a equal to aij, ai, a naught are the input data are given, which we call it inputs. Inputs. We make appropriate assumptions, of course, we make appropriate assumptions. One of the assumption is the ellipticity, otherwise it is a very general second order linear equations. So, one of appropriate assumptions. Okay. So, on the data you have to make such assumptions on the data. Okay. So, first we will start with, we will come back to this general case a little later. So, first consider L naught of u equal to here you have aij. So, you have your aij of x minus dij of u equal to f. That means you are assuming a equal to 0 and identically your a naught identically 0. So, we will discuss these kind of things are also assumption. So, let me start with the definition. We will give some motivations. The operator L naught is called elliptic in fact uniformly elliptic. Is a very strong condition to make it into an elliptic class, uniformly elliptic if there exists alpha positive such that aij xi I psi j. Of course, I said there is summation always. So, whether I make it in a repeated indices, the summation is used on II. This should be greater than or equal to alpha into mod psi square. This psi is a vector for all psi is in Ri. Okay. So, that is why it is a, so this is an important condition. So, one assumption which you make it. So, we are considering elliptic operators only in this course. So, we also have the boundedness condition, other assumption. Boundedness of Aij. Okay. So, basically it says that Aij belongs to L infinity of some domain. We are already dealing with some domain omega is in Ri. Okay, open set. Okay. So, this assumption we may write it in different ways. Various ways you can write these assumptions are written in different ways. Like that, some places we use it. Some books you may see that Ax of psi is less than or equal to m into mod psi. That is one way of writing. So, you will see different ways of doing that, or you write it Ax psi sorry Ax psi, which is a vector in Rn. So, you have Rn in a pod less than or equal to m into you can write it mod psi square. So, basically with ellipticity and this assumption you can combined way you can write, that is how many books will write. Combined way write the assumption as some alpha into mod psi square less than or equal to Aij psi I psi j less than or equal to m into mod psi square. So, you will see books writing the assumptions in various. So, there exists alpha m positive, and this should happen for all psi in R. Okay. So, if you look at it, this is basically the ellipticity is essentially uniform positive definiteness, essentially the positive definiteness of the matrix, uniform positive definition, positive uniform positive definiteness of Ax, you see. Now, just a digression here, just I want to tell you something. If A is constant matrix, is a constant matrix, and positive definite, then A is invertible and Ax equal to B is uniquely solvable, you see, solvable. And other remark is that A has n up to counted up to multiplicity, has n positive eigenvalues. So, you see positive eigenvalues. Okay. So, you want to study a similar thing. So, you expect, so that natural thing expect L naught of u equal to f solvable. Of course, there are difficulties which you want to remark when you go to, because now the solvability is in a function space, infinite dimensional situation, and also existence of eigenvalues. Whether we can do existence of eigenvalues. Of course, what we are going to do it for the weak formulation. But let me make one remark again here. Even for the classical case, look at this equation minus Laplacian. This you have studied in our not part 1, our first course on partial differential equations in omega, and u equal to g on d omega. So, this you can indeed divide u into two form, v plus w, with minus Laplacian of V equal to F and V equal to 0 on d omega, this is in omega, and then minus Laplacian of W equal to 0 in omega and W equal to G on d omega. The remark what I want to make, as far as this equation is concerned, this is the study of potential theory. And when we are looking for V in, looking for if V in C2, that will imply essentially F is continuous. So we expect a solution for Laplacian of V equal to 0 F with F continuity, but unfortunately we need more stronger assumption. Just continuity of F is not enough. Continuity of F is not enough. Okay, so this is separate, and we need what is called F. So maybe I will write it in the next page is coming, because what we need is F should be in some Helder continuity. So we need little more assumption. So even for the solvability, the potential theories. And regarding this equation is concerned, in the first course on PDE we introduce Perron's method, and for the existence need regularity of omega. You see, regularity of omega. So you require assumptions even in the classical case to do it. Okay. So exactly what we have done for the splitting, okay. So what so again the same thing can be done due to linearity. Due to linearity, here also we can do L naught of U equal to F, and then boundary condition. The boundary condition can be U equal to G or du by d nu equal to G, or something like that, the mixed boundary conditions, Robin boundary conditions, it can be anything. So we can split, you can again write U equal to V plus W with L naught of V equal to 0 F plus boundary plus 0 boundary condition, whatever be that linear situation, and L naught of W is equal to 0 with a plus boundary condition. That means non-homogeneous. Here it is homogeneous boundary condition. Homogeneous, here it is non-homogeneous. This is the non-linear feature, you can do that conditions here. Now, so we will the same thing can be what Laplacian done. Now I want to recall some motivation which we have. So we will how to do the variational formulation. So recall the motivation we have given during the first part of this course. Okay. There we considered the Poincare functional. If you recall the Poincare functional, half of grade u square or half of grade v square with v in C1 naught of omega bar. And just recall the requirement of this is the right time on the motivation time, requirement of completing C1 of naught of omega bar with respect to this Dirichlet norm with respect to grade V square whole power half in, so that means, or with respect to H1 norm, whatever you call it, okay, and which gives you your space H1 naught of omega bar, H1 naught of omega. So that is a Sobolev space we will be using to study these equations. Okay, so okay, so let me write down. So let us consider slightly general function. Okay. So now consider little general, more general. Consider the functional. So I am just, this is already explained in a slightly more general, is equal to half of grade V square plus half of integral V square. This is over omega. This is the energy functional. For example, if you study elasticity system, you will see that this is a strain energy functional in applications. Okay. So such energy functionals or cost functionals, all that will be coming to you. Okay. So what do you want to do it? So what is the problem which you have taken for motivation? Problem is because you want to minimize the energy for all possible admissible class of functions. So you want to find u in x. X is, let me denote by C1 naught of omega bar. So I am just recalling what I have introduced, and now because we have now the Sobolev spaces, we can do everything now here what you wanted to achieve. Okay. So you want to find the f of u is equal to minimum, you want to solve this problem, or infimum where v in C1 naught of omega bar with f of v. Okay. So what we have done is that if u is a solution, if u bar is a solution, if u bar in x is a solution, what you do is that you compute your f prime of u bar should be 0. That is the kind of calculations you have done. But what is f prime of u? F prime of u bar is a mapping from, because it is a Fresher derivative, it is a mapping from something like x. That is a question you have to, where do you want to do that one, okay, which will make it very clear, and you can see that f prime of u bar acting at v should be integral of grade u bar grade v plus integral of v, u bar v is minus integral of f v. I call this to be AUV because this is the notation I am going to use it, and this is a bilinear form. Bilinear form. And thus this gives you, we need to study find u bar in x such that your AUV equal to FV integral of FV for all u bar v for all v in H1 naught. Okay, for not H1 naught yet, I just want to tell why you need H1 naught. Okay, so for all v, so in x. So, this is essentially Rees representation theorem, because this is the norm there. So, it is essentially Rees representation theorem. Rees representation theorem but to apply Rees representation theorem you need the completion, we need the completion of x with respect to the grade norm or an H1 norm, okay, completion of x which is H1 naught. So, we have for this Laplacian, which we will do it for general elliptic equation. So, since so this equation is also in because this space X is dense in H1 naught of omega. So, that equation is actually so we get it in H1. Simply this find a u bar of v, I will sometimes I may not use u bar, you just integral of f v for all v in H1 naught of omega, and you look for your u bar is in H1 naught of omega. So, you can basically for this is almost your Rees representation, but we are going to do it for more thing. Okay. So, the same thing now for the L naught, for L naught we can do the same thing, we can go ahead with the, for L naught we have to define, we define AUV is equal to integral of Aij of x du by dxj and dv by dxi over omega, and this for all uv in H1 naught of omega. So, one remark which anyway we are going to formalize everything, if A equal to Aij symmetric, this is an additional assumption, end of it we do not need it, we will study, but then there are advantages if you assume symmetric. If A is symmetric, and of course with boundedness and ellipticity, boundedness, ellipticity, this is a some simple exercise which you can show, then AUV defines a new inner product, defines a new inner product. The earlier one is say for the Laplacian case, because Laplacian is a special case of Aij. When you take, this remark probably I did not make it, if Aij is equal to delta ij, you get L naught is equal to Laplacian. Okay, we are not can see that. So, the Laplacian is a special case of L naught. So, when you have Laplacian, it is a normal product, it is the same inner product of H1 omega. So, it is a kind of immediate application of your Rees representation theorem, but when you have a symmetry of A, you have defines a new inner product in H1 of omega, which is equivalent to due to ellipticity. So, symmetry is needed to prove that it is an inner product, and use your boundedness and ellipticity which is equivalent to the the given inner product on given inner product on H1 of omega. So, just prove it. It is a trivial thing, but it is nice to get familiarized with such theorems. Okay. So, you get the same topology, same standard topology, and you can get in there. So, basically what you are trying to prove is basically you are going to again apply your Riesz representation theorem with respect to the new inner product, okay, of AUV. Okay. So, that is what you are doing, and that is essentially the content of Lax-Milgram lemma, content of Lax-Milgram lemma. Okay. And which we will be doing it. Okay. So, this came out. I want to make one more remark here, and then I will end this talk, and then we will consider. So, one more remark. Suppose U is a solution, suppose U is the solution of this AUV for Laplacian. You can apply for the general elliptic case also, integral of grade U grade V plus integral of Fv equal to integral of uv equal to Fa. Okay. So, this is what you are going to do it, u in h1 naught of omega, and if u is in C2 of omega, if, so you are assuming a more regularity, then I can do an integration by parts C2 say omega. So, then I can do an integration by parts to show that minus Laplacian of u plus u minus f over v equal to 0 over omega. This is for all v in h1 naught of omega. And this is a dense, you note that this is actually a dense space in dense in L2, dense in L2 of omega, keep that in mind. And since u is in C2 of omega, this is in L2. Therefore, this equation is valid in L2 of omega. That implies, so you have an integral of a 2 L2 functions for all v in L2 of omega. So, this equation is valid means for all v in L2 of omega. That implies minus Laplacian of u plus u equal to f almost everywhere in omega. And if you have the continuity of f implies in the other case you need f is in only L2. So, we are going to study that f is in L2. So, implies minus Laplacian of u plus u equal to f point wise. So, you get a point wise thing. Okay. So, that is why called, so your PDE is obtained by making an additional assumption u is in C2 of omega part, and this formulation star, this is your strong formulation. So, star is called the weak formulation of the PDE double star of double star. So, you get your PDE only when you make further assumptions. So, that gives you an immediate thing, your weak formulation is actually more closer to your original problem. So, the weak formulation is not something artificially created from your thing, but then we also need to use a strong form. If possible you want to get it, use the rich theory available for that one. So, we have to, when u is not smooth, you basically have to stick to your weak formulation, and that is why we need to study that. Okay. Thank you. So, we will continue the lecture by giving some abstract formulation. Thank you.